You know that tensor analysis is the indispensable mathematical tool for the study of general relativity. So in this playlist, I have shared my videos which I have actually earlier uploaded in the playlist mathematical physics. So definitely I will suggest you to go through all those videos on tensor analysis before we will start the study of the proper theory of general relativity. But we need some more tensors for the study of general relativity. Some specific tensors like Christoffel symbol, like the idea of geodesic, the concept of Ricci tensor, Einstein tensor, okay, energy momentum tensor. These are the tensors which we need to understand the concept of general relativity. So first of all, we will provide videos on these tensors, and after the completion of the concept of these tensors, we will start to study the Einstein equation, or you can say the Einstein's field equations in general relativity, and discuss the complete theory of general relativity. So in this regard, today I am going to introduce you a very important symbol that is called Christoffel 3 index symbol. In fact, first of all, you have to know that these Christoffel symbols are not actually tensors, because you know any quantity will be a tensor only when it follows a particular law of transformation. When you pass from one coordinate system to another, a tensor quantity follows a proper law of transformation. But you will see that these Christoffel symbols do not obey the laws of tensor transformation. So we simply say that Christoffel symbols are not tensors. But in the last of the lecture, we will also learn that under a certain linear transformation of coordinates, these Christoffel symbols get transformed obeying the transformation law of tensors. In that condition, particularly in that linear transformation of coordinate, we call these three index symbols pseudo tensors. So this is a very important fact that Christoffel symbols are not tensors because they do not get transformed obeying the transformation law of tensors. Okay. So in this lecture, we will first of all define these Christoffel symbols, okay, and then we will see how they are actually get transformed. In fact, Christoffel symbols are of two types, which are called Christoffel symbol of first kind and Christoffel symbol of second kind. This is just a definition, so you have to remember it. The Christoffel symbol of first kind is denoted by this symbol. Inside the square bracket, you have to write these indices jk, l. Here, j and k are associated. Okay, there should be not any comma between j and k. And this is just equivalent to gamma l jk, l comma jk. You can see here that l and jk here are covariant indices. Okay, and this is defined as 1 over 2 times del gij by del xk, okay, plus del g kl, where kl are covariant indices, by del xj minus del xjk by del xl. You should remember this expression by a technique. You can see, in fact, here, first of all, we take the subscript L. covariant index L, and then J, and take its partial derivative with respect to xk. It means the index which is in ahead of L and J, that will be in here. Then you should take K and L, okay, and finally this JK will be taken at the last term, and my minus sign will be before that, okay. In this in this way you can remember it. Now the Christoffel symbol for the second kind is denoted by this symbol. In fact, here the three indices L and JK are written inside a curly bracket. Mark it. Here the symbols are indices are written inside the square bracket, but here it is written inside a curly bracket. And L is taken as a superscript, or you can say contravariant index, and J and K are taken as the subscript, or you can say the covariant index. And it is equivalently written as gamma superscript L and subscript JK, or contravariant index L and covariant index indices J and K. And this is defined as 1 over 2 GLM times del G JM. Here JM, you can say these are the covariant indices, by del XK, del G KM by del XJ, and minus del G JK by del XM. You can see here actually this what are these G's? You know, these are the fundamental tensor, and every G here actually represents the fundamental tensor, okay, or you can say the metric tensor. So in this way we define the Christoffel symbols in terms of the metric tensor or the fundamental tensor. In fact, in my previous videos I have already discussed this metric tensor or fundamental tensor in very detail. So these are the expressions which define the two types or two kinds of Christoffel symbol, and you have to remember it, okay. Now you know that these metric tensors, that is this GJK or GIJ, you know, these are actually the symmetric tensors. So utilizing the property of symmetry of this tensor GJK, it means when you say that GJK is symmetric, then it means GJK is equal to GKJ. When you will interchange the indices, the tensor will not change. So utilizing this very symmetric property of the metric tensor, you can say that actually the Christoffel symbols of the first and second kind both are also symmetric in the indices J and K. So for the first kind of Christoffel symbol, you may write that JK comma L is equal to KJ comma L, or gamma L comma JK is equal to gamma L comma KJ. Similarly, the second kind of Christoffel symbol is also symmetric, and so with respect to the indices J and K, so this is written as superscript L and subscript JK is equal to superscript L and subscript KJ, or you can write gamma contravariant index L covariant index JK is equal to gamma L KJ, okay. So these results actually shows that Christoffel symbols are also symmetric with respect to the indices J and K. These facts are very important for your objective type question, and also to understand the concept of general relativity wherever it will be used, okay. Now let us see how these two kinds of Christoffel symbols are related to each other. Okay. If you talk about the second kind of Christoffel symbol, that is this gamma LJK, this is related to the first kind of Christoffel symbol by this relation. This second kind Christoffel symbol gamma LJK is equal to GLM times gamma M comma JK. Here you can see the symbol in the LHS of this expression is the second kind of Christoffel symbol, and in RHS this is actually the first kind of Christoffel symbol, and this is the relation between them. Now let us prove it. In fact, you have seen the definition of this first kind of Christoffel symbol, that is gamma L comma JK. This is equal to 1 over 2 times del G Lj by del xk plus del G KL by del xj and minus del G JK by del xl. You have seen the definition. Now, you know that the free indices may be changed. So here, if we will replace this L by M, then what we will our result? So in each term where there will be L, now replace that by M. So you can see the LHS will be gamma M comma JK, and that will be equal to 1 over 2 del G MJ by del XK. Here L has been replaced by M. And in the second term 2, you can see this will be del G KM by del XJ and minus del G JK by del XM. Okay. Now let us multiply both sides of this expression by this tensor GLM. Okay. So LHS will become GLM times gamma M comma JK, and that will be equal to 1 over 2 G time GLM times this much. Okay. Now you know that this tensor, that is the metric tensor GMJ, is symmetric, and so GMJ will be equal to GJM. Okay. So instead of GMJ in first term, you can write GJM. So you can see it here. Okay. And other terms are attached. But you can see the definition of the Christoffel 3-index symbol of second kind, that this expression is nothing. This is simply the Christoffel 3-index symbol of second kind, and this can be written as gamma LJK. Okay. I am not telling always superscript and subscript. I am simply giving the reading LJK, but you can see here that L is the superscript or the contravariant index, and J and K are the covariant index. Okay. So in this way, you can see that I have proved that gamma LJK is equal to GLM times gamma MJK. Okay. But I have proved it. For university examination, this will be needed to understand each and every step, because you have to prove it. Okay. But in the study of general relativity, we will need this expression directly. So you should also remember these relations. Okay. Now let us see how we can relate the Christoffel 3-index symbol of first kind with the Christoffel symbol of second kind. In fact, this gamma LJK is equal to GLM times gamma MJK. Okay. Now remember this result, and now I am going to prove this. For this, we will start with the definition of the Christoffel symbol of second kind. You know, you have just seen that the Christoffel symbol of second kind is denoted by the symbol gamma LJK, and it is defined like this. This is 1 over 2 GLM times this much. You have just seen. Okay. Now again we will interchange L and M. It means where there is L we will write M, and where there is M we will write L. Okay, this can be done. So here there is L, you can see in LHS. So this second kind Christoffel symbol will be now written as gamma MJK, and here 1 over 2 GML. Instead of L I have written M, and instead of M I have written L. Similarly, in the different terms inside this bracket, L and M have been replaced. Okay. Now let us multiply this expression both sides by this metric tensor GLM. Okay. So after multiplication, our LHS will become like this. This is GLM times gamma MJK, and that will be equal to 1 over 2 GLM times GML. Here you can see GLM, here LM is the covariant index, and here ML are the contravariant index. Okay, and times this much. Okay, but you know that this product is equal to the Kronecker delta LL. It means both indices are equal, and you know Kronecker delta LL is equal to 1. So this product, that is G covariant indices LM times G covariant indices ML, that is equal to 1. So this product is equal to simply 1 over 2 and times this much. Okay, but see the definition of the Christoffel symbol of first kind. You can see this is nothing, this is simply the Christoffel symbol of first kind denoted by the symbol gamma L comma JK. So in this way we have proved that the Christoffel symbol of first kind gamma L comma JK is equal to GLM times gamma M JK. Okay. So now observing these two results, you can see that when you passage from one Christoffel symbol to another, that is when you passage from the first kind of Christoffel symbol to the second kind, or the second kind of Christoffel symbol to the first kind, then the process is just like raising and lowering of index. You can see it is just like raising and lowering of index. I have provided already a video on raising and lowering of index. You can see my previous video, and so this relation can be written just on the basis of the process of raising and lowering of an index. Okay, so I think you have clearly understand how these Christoffel symbol of two kinds are defined and how they are related. Now actually we will illustrate this definition by a proper example, and this is a very important example for your examination purpose. So see this problem. Here we have to show that the sum of the Christoffel symbol of first kind defined by this JK comma L plus LK comma J, or you can say that gamma L comma JK plus gamma J comma LK. This is equal to this much. This is partial derivative of GJL by del GJL by del XK. This problem can be easily solved. Only you have to remember what are the definitions of the first kind of Christoffel symbol. Applying the definition and certain property of symmetric tensor, you can easily prove this result. Let us see. So by definition we know that this first kind Christoffel symbol jk comma l, which is just equal to gamma l comma jk, this is equal to this much. This is just the definition. And in the similar manner, you can say that this first kind of Christoffel 3-index symbol lk comma j, which is denoted by gamma j comma lk, that is defined like this. These are simply the definition, you can see. Now we have to find the value of some of these two Christoffel symbols. So let us add these two. So this jk comma l plus lk comma j, which is equal to gamma l comma jk plus gamma j comma lk. Now see equation 1 and 2, and let us put the values. So you can see this gamma l comma jk is equal to this much. So I have substituted its value. When you will add the RHS of equation 1 and 2, you can see this 1 over 2 is a common factor, so I have taken it common. And this is the expression which have been taken from equation 1, and this is the expression which has been taken from equation 2. But you know that this metric tensor GJK is a symmetric tensor. So GJK and will be equal to GKJ, and GLK will be equal to GKL, and GLJ will be equal to GJL. So now let us see this minus del GJK by del XL, okay, minus del GJK by del XL. And here see this term, I am marking by this cross sign. Since GJK is equal to GKJ, okay, and therefore both of these terms are same, but sign is opposite. So this will actually cancel by this term, okay. Again let us see this last term, del GLK by del XJ, okay, and so mark it. I am writing here a dot and here also a dot. See these two terms. Since GKL is equal to GLK, so this term which is I am marking by this dot, and this term which is I am marking by this dot, both are same but sign is opposite, so this will also cancel, okay. And again you can see this GLJ and GJL both are equal. GLJ and GJL are equal. So these two terms which is marking by this arrowhead, these will get added. And when we will add it, this will be 2 del GLJ by del XK, and that 2 and this 2 in denominator will cancel out. So finally what you will get? Finally we will get that this is del GJL by del XK. So in this way, if you have the definition of the Christoffel symbol of first kind in your mind, you can easily solve this problem, and I think you have clearly understand this solution, okay. Now I will talk about the transformation laws for the Christoffel symbols, okay, for both types, that is for the first kind symbol and for the second kind symbol. In fact, here I have written the transformation law obeyed by these symbols directly without proof, because our aim is to remember this for the study of general relativity. Although when you will consult any textbook, you may get the proof of these transformation, but I have not actually followed that. I have written the transformation symbol directly. You can see, if you want to write the transformation law of the Christoffel symbol of first kind, you know this gamma LJK, This is the Christoffel symbol of first kind. If this gamma, L, J, K are the Christoffel symbols in a coordinate system having coordinate, let us say x, and its components in the another coordinate system, let us say x prime, is, let us say, gamma prime sigma mu nu, then this gamma prime sigma mu nu will be equal to gamma L J K. Now this expression has been written just on the basis of the transformation law obeyed by a tensor. Okay. So if you have watched my videos on the different tensors like covariant tensor of first rank, second rank, okay, and in general nth rank, the contravariant tensor of first, second, and nth rank, then you have definitely an idea of the transformation law of tensor. So obeying that, you can write this first term. Okay. Here this will be del xj by del x dash mu. See here, when you will take this index, you have to take this index in denominator. Okay. And del xk by del x dash nu, and times del xl by del x prime sigma. Okay. But this is the extra term. You should remember it. Here the first term has been written just on the basis of the transformation law of a third rank tensor, a covariant tensor. Third rank covariant tensor. The first term has been written like that, but the second term is the extra term which comes here, and due to the presence of this second term, you say that this Christoffel symbol does not transform like a tensor. If this second term will be not present, then it will just transform like a tensor, and then it will be called a tensor. But in its transformation, this second term is non-zero. So this second term is del 2 by del xj by del x prime mu times del x prime nu times del xk by del x prime sigma gjk. Okay. So I have written here, you can see it is clear that Christoffel symbol of first kind do not transform like tensors unless the second term in RHS is 0. If this second term will be 0, then you can say that this quantity is transformed just like a tensor. Okay. So, but in actual situation, this second term is not 0. So you can easily say that the Christoffel symbol of first kind does not transform like a tensor, and that's why we simply say that Christoffel symbols of first kind are not tensors. These are not tensors. Okay. Now you can see the transformation law followed by the Christoffel symbol of second kind. You can see this gamma LJK. These are the Christoffel symbol of first kind in a coordinate system, let us say S, in which the variables are x, and the second is actually S prime, and in it the coordinates are x dashed. So if the components of this quantity gamma LJK in another coordinate system is gamma dashed lambda mu nu, then this is transformed like this. Again, it is evident that the Christoffel symbol of second kind do not obey the tensor transformation law unless the second term in this equation B2 is 0. Okay. So this clearly indicates that the Christoffel symbols of second kind are not tensors. Okay. But as I have told you that in a very special case of linear transformation of coordinate of this type, xj equal to aj mu times x dash mu plus bj, if there is a coordinate transformation defined by this linear combination of quantities, where in fact a, j, mu and bj are constants. In that condition, you can see this second term will vanish, this will be 0. And if this second term will be 0, then what will be the transformation law obeyed by the two kinds of Christoffel symbol? For the first kind, you can see that transformation law will be like this, and for the second kind, this transformation will be like this. And these two equations clearly imply that these symbols in this condition obey the transformation law of a tensor. But only when you talk about the linear transformation which I have defined in this equation C. Okay, so you can say that these two equations C1 and C2 indicate that the Christoffel 3-index symbols transform like tensors relative to the linear transformation of coordinates of the type C. And actually in this condition, the Christoffel symbols are called pseudo tensors, not tensors but pseudo tensors. So this is a brief account of the Christoffel symbol, and I think you have definitely understand it, because and you must remember these things for the study of general relativity. Okay, thank you very much.